Good afternoon, everyone. My name is, as you just heard, Younes Lusayev, and unlike my colleague Oscar, this is actually my first time in Korea ever. So I arrived yesterday, so I'm very excited about that. And thank you for having us here at KISTI. It's a pleasure to be here and to be presenting for you. I started at Systicon in 2006, in the beginning with software development, training and consultancy work. And over the years I have moved from development. There are people who knows how to program much better than I do, but more to the field of the interface between the tools, the analytic lifecycle management, and the customer use to understand and to help customers how to realize business value from the capabilities that we offer with Opus Suite. And this is a really interesting field. Before that, I was I worked as a consultant with more bigger ERP program implementations and integration systems. And I have a Master of Science degrees in Systems Engineering from the Royal Technical University in Stockholm. I first wanted to build airplanes, but that proved to be too complicated, and I was more fascinated by mathematics and optimization and things like that. I will continue what my colleague Oscar just talked about and try to put this into the context of the Opus Suite, and to see also more practical with some demonstrations how analysis could be performed, and to give you also a flavor of how we work with the tools and what kind of questions we address through the life cycle. So, without further delay, let's get started. I will retake some of the points that Oscar talked about. I think that will be okay, because it's always good to repeat things. So we're looking here at something called the availability performance, and that was things that Oscar mentioned. And the requirements on availability performance are governed by the operational requirements, because if we don't know what we will use our systems for, we don't know what the availability performance will be like. How demanding are the missions? What readiness is required, etc. And as we have seen also, availability performance can be broken down into the classical RAM-C properties of reliability, maintainability, and support effectiveness, and of course cost. And these are divided upon some entities that are key in logistics support analysis, which is of course the technical system, but also the support organization. So together they will constitute this field of RAM. So in order to affect and impact availability performance, we need to work with these entities. And typically we have on the system side the logistics support analysis, conducted often by the manufacturer and or the supplier of the technical system. And on the other side, we have the support response, which is, it could be the manufacturer, the industry nowadays too, talking about PBL contracts and things like that. But more often this is close to the operator side, to understand how to build up the support, logistics support organization. But there is also a price here to be paid. How much is availability performance allowed to cost. Because if we had an infinite amount of money to spend, we could have tens of thousands of spare parts and resources and systems that could help us make sure that the operational goals are met. But unfortunately, that is not the case. So, availability performance and sustaining availability performance is not a one-off task. It needs to be addressed throughout the whole life cycle. We cannot be satisfied with saying that availability performance is achieved during the development process of the life cycle of the system and then never come back to the question. This needs to be taken care of all along the way. And in order to be able to control the availability performance, we must give ourselves the best possible means in order to do so. And we talked, I don't understand much Korean, but from the first presentations made, I was retaining anyway that data and big data and the use of analytics on data gives us a lot of information. And with that information, we can do analysis. So, in order to be able to address and answer important questions along the life cycle of our technical systems, we need to give ourselves the means to perform sensible analysis. But each phase during the life cycle has different questions to address. Different questions that requires different types of data and different details of data. So, if you have this information, you have the data, you have the tools and the processes in place, you're on the right track to address these questions and to become not only system effective, but also cost effective. This picture Oscar described perfectly just before me, and I just want to retake it once more to say that Opus Suite provides the tools and the analysis capabilities required to support a successful and continuous implementation of analytic lifecycle management throughout the system's whole lifecycle. And now we're going to see some examples of the capabilities of the Opus Suite. In the world of Opus Suite, the model is in focus. So the purpose of the model is to mirror realities and the elements of the world that we are navigating in this case, the technical system, the operational requirements, the support response, etc. So typically you start out with a very basic model, but since reality is complex and you have many different types of questions to address, different topics as you move through the life cycle, we like to expand this model in different directions or in many directions. And this is the same way that Opus Suite is built up. So that you have the possibility to work on a very focused basic model, but you can expand it in many directions, making use of the types of analysis that you require for your specific question to address. So if you have the ambition, as we have, to create a tool and a model that should be supporting decisions throughout the life cycles, you must be prepared to have a lot of capabilities available. But it's not only the model that could start out and the functionality in Opus Suite that can start out in a basic way and gradually expand. This goes also for our main entities in this field of analytics: the support organization, the technical system, and the operations. Different phases and different questions require different levels of details and the granularity as well. So, to exemplify here, we can see if we take the technical system at its simplest description, you can see the technical system as just one unit with the properties of, with some basic RAM properties. How often does it have to be maintained, and how long time does it take to be maintained? And let me just shortly take a break here to just focus on, of course, the technical system needs a lot of technical properties to conduct a specific task. If you are operating at night, you might need night operating equipment, etc., etc. This field is also, of course, impacting on the system effectiveness. But that is another discipline, technical capabilities. What we are talking about and what we are primarily focusing on is then the availability, not what the system can do, but when the system can do it. And in this world, we can describe the aircraft as when is the system available, when does the system need to be down for maintenance, and how long time does it take. This is the simplest way of describing the system. But this is not enough moving forward, because we are gradually getting more information about our system, and we can break down this information step by step until we get a meaningful and very extensive description of the system. But it will always translate back to the same properties. How often does the system need to be down, and how long time does it take to maintain it? Because except for those, the system will be in ready condition. The same way with the support organization that will support. The support response will boil down to one thing. What is the delay time of the support response? Once the system needs maintenance, how long time does it take before you can start maintaining the system? This is the mean logistic delay time, and is at the end of the day, the parameter that is described by a more complex organization. And to understand the support response in a more complex organization, you would have to need analysis in order to understand the resulting weight for logistic resources. When you're at the beginning of a project and you don't know exactly about how much the system will operate or the operational profile, start out with a very simple model, an assumed operational profile. As you move further through the life cycle, you will gather more information. Then you can expand the model and create a more complex profile in order to understand the performance in this. So I hope I get the message out here. Always does not, or I rephrase, don't wait for having the complete and exact information in order to start to do analysis. You can do a lot with very little early, and always come back. Since we are doing this continuously over the whole life cycle, we will always add more information as we are moving along. So, enough theory, and now we will go into more concrete examples and some demonstrations, and I hope that the demonstration gods will be with me, so I'll try to switch here between the tools and the presentation. So we start our journey through the life cycle in the conceptual phase, and in this case we we have an idea about the capability that we want to establish, but what are the requirements on this capability? And what does this demand from the technical systems that we need to realize it? So we are setting up some operational contexts, and we must think about what is it. These contexts could be looking different depending on if it is a naval operation group we are planning to establish, or coastline defense, airspace surveillance, search and rescue, etc. And once this is defined, we need to understand what should be the properties of the systems realizing this capability. So, to make things easy, I like airplanes, so I always exemplify by airplanes, but this could go for any system. So if you prefer boats or land vehicles or anything else, so you can try to imagine that as well. But we will use an aircraft as an example here. And what are the requirements on this aircraft in order to be able to satisfy a certain operational demand? We don't know nothing about the aircraft at this time. We don't know the idea of an aircraft, and we need to be able to establish some kind of overall requirements on the RAM properties of the aircraft. Could you do any analysis with only this information? Yes, we can, but we need to establish some kind of overall picture in order to get the ideas of what these could be. And to exemplify that, we model our aircraft as a very simple system, a product variant here, our aircraft system. But we also need to understand some more about how many aircraft do we think with these properties we need in order to satisfy the operational requirement, and also what should the logistics response be when this aircraft needs maintenance. So the key questions that we want to know is, what requirements on the aircraft can we accept? How many aircraft do we need to fulfill this operation? And what is the limit for the response time of the support?